Hi, my name is Miloš and welcome to Element 14 Presents. Today I'll show you how I converted a standing desk with a crank to an electric one for just $50. Before I made this desk, I just had a regular sitting desk, and this is actually that same tabletop from it, as you will see in the video. But one night on Facebook Marketplace I found an IKEA trotting desk with this mechanism for just around $100, and I thought that was a steal. Even if I had to crank it up and down with this thing, it was still a really good price. But when the desk arrived, I saw that for the crank it's just a 6mm shaft that you need to run on to one or the other direction to lift the desk up or to lower it down. So I thought, why not convert it to an electric desk by myself? Let me show you how I actually did that. Let's first see how the desk itself works. Near one of these legs there is a 6mm hexagonal hole that we turn with the crank that comes with the table. This is what makes the table go up and down. This is of course the same shape and size as the 6mm Allen key, so we can either cut our shaft out of the Allen key or out of the crank that came with the table. We will connect a motor and an encoder to this hexagonal shaft, and we will also need some kind of a physical interface with buttons and the screen, as you've already seen in the beginning of this video. I put the motor and the encoder on opposite sides of the table mechanism. If you're gonna do that, also make sure to cut the shaft long enough so it reaches both the motor and the encoder. The type of encoder I used is called an incremental encoder, and the output signal of that type of encoder looks like this, a square wave. For the one I'm using, there will be 20 pulses per rotation, so we can then translate those pulses into actual table height. If you look at just this signal, you couldn't tell whether the motor is spinning in one direction or the other. That's why most of these encoders have two outputs, A and B. It's the same number of pulses, but they are phase shifted. Depending on which one of them is high first, we can tell the direction of the rotation. With this we can track the relative position, but we don't know the absolute position if we don't know the starting position. This is why we need a known home position, and we're gonna get that using a micro switch. This is why I added a micro switch to the leg of the table that gets triggered once the table reaches the bottom, and we will just gonna name that the home position since we know the height, and track the relative position from there. We will also use this micro switch as a limit switch, so the table doesn't try going lower than it's physically possible. The first thing that I had to figure out before making this desk is what kind of motor I'm gonna use. My initial thought was to use something like a windshield motor since they're rather powerful, but then I thought, is there any kind of a device that I use pretty much on a daily basis that's actually torquey, handheld, and runs on 12 volts? And there actually is. Those are your common handheld drills, so I ran a test. I had an old Lidl Parkside drill that's running on 12 volts, and I decided to test it out with the IKEA trotting desk, and you can see that here. And as you can see, it can go up and down without any issues. Even better, the tip of that motor actually has the same hexagonal 6mm thing like the IKEA trotting desk crank. So it was a match made in heaven, pretty much. Let's disassemble that drill now, take the motor out, and see how it's running on the bench. So this is the motor I've gotten out of the drill with its gearbox and the 6mm hex coupling that's perfect for our IKEA table. Here I have a power supply set to 12 volts and 3.1 amps, which is the maximum for this supply. So let's try powering on this motor and see what happens. As you can see, the power supply goes into overcurrent protection immediately, and the motor doesn't actually spin. So why is that happening? Is the motor bad? No, if we try something like this and try the battery from the drill itself, let me just check the connections. Here we can see. As you can see, the motor is spinning completely fine, but you've seen how big the spark is. That's because the motor, when it's in a standstill, and since there is a lot of torque that the motor needs to go through to spin up this gearbox, the current it needs is rather high. So we can't just use a simple relay module like this to turn on the motor. We will need to use something like this, a proper motor driver where we can soft start the motor and raise and lower the desk. This will be even more important when the motor is under actual load for lowering and raising the desk. Let's talk about the proper setup for this. As you've seen, the power supply can't really handle all of that inrush current. The drill just draws too much power. So what we actually need to do is ramp up the power slowly so that we don't have that massive current spike. What we want to do is actually something like this that I'm gonna play now. In that clip, you've seen that if I go on the trigger here rather slow, you can see that I can get it going through the power supply, but if I just press it as an on-off switch, the power supply is just not strong enough and it will even burn out through the video, as you will see, but we still have the batteries that came with the drill. Before we move on, can you just take a moment and appreciate this beautiful spark here? Just look at that blue glowing light, it just looks amazing. I'm mesmerized by it. Too bad it can be at constant color like that, to use it instead of some RGB LEDs. Let's go now through electronics for a proper setup with a motor driver and then finally see how this desk came together. You've seen what happens when we connect the motor directly to the power supply without anything in between. We just overload the power supply. To combat that, we will use a motor driver, so we can gradually increase the power at the beginning and then just go full speed so we can get the maximum possible speed. To control the motor driver, we need two PWM signals, and to get those, I will just use a small ESP32 board that I have laying around, because it's Wi-Fi capable and it's more than powerful enough to do stuff like this. To make it a complete project and a standalone unit, we also need some kind of a buck converter to lower the 12 volts that we will use for the motor to 5 volts that the ESP32 needs. Also, for the sensor, we will just use a simple incremental encoder as you've seen in the drawing, and I will add an end-stop switch just as a safety precaution so it can actually home like an old school 3D printer like your Ender 3 Pro. Besides that, we will also have some buttons just for physical controls and a small OLED screen so you can see your height and what the device is currently doing. Before we test everything on the bench, we need to write some software for the ESP32, so that's what we're gonna do next. We're in Arduino IDE now, where I've written the code for the ESP32. You don't really have to use an ESP32, I had one laying around and I think it's not a bad thing since it's already Wi-Fi capable, so just have it at a static IP address, so at the future if I want to automate it in any way, shape or form, I can do that easily. So I've just put it to this static IP address and it will always connect to that address every time the device restarts. Besides that, at the top of the code you can set up all of your pins depending on the board you're using. So these are the motor pins, so these are for the PWM for the motor driver. You have the encoder pins, you also have the I2C pins, button pins and so on. It's pretty self-explanatory. AI of course helped with writing this code since there was a lot of things to write when it comes to especially the web interface part, like the things you can see here probably and here. Yeah, I mean that it just saved me a lot of time, and in the end I ended up with an interface that looks like this. We have the manual up, manual down controls, we have the stop and we have the home button here, and we have the free memory buttons. For the physical interface I have the manual up, manual down buttons, and we have these free memories. Here you can also change these memories on the fly and they will stay saved between power cycles. You can also change your minimum maximum height, and there are some helper functions here for the calibration or for testing when you're trying to calibrate your device if you want to recreate this, because I had some issues with an encoder and you can just test it out more easily like this. Let's see how all of this works together connected on a bench. With the electronics and software complete, now we have our final setup before we put everything together. So here is the ESP32, a small display, the motor driver, we have the motor with the gearbox and an encoder to measure the position. We also have the homing switch. We don't have the buttons that you've seen, but this is just a test to prove all of the functionality, so I will use the web interface. So if you press manual up, you can see that the motor now Let me just turn it off so you can hear me clearly. You can see the motor spins up without any issues, without the power supply issue as you've seen before, because we have that wrap in the beginning. And if, for example, if we click home, the motor will start going down, and once the end stop is hit, this will say 70 centimeters because it's just set up like that. And that's the homing position. And now, for example, if we click memory 1, you will see that it says M1 here, and it will go to a set position like 72 centimeters, for example, and so on. So the whole setup works. The only thing left to do now is to put it all together and fix it on the table. There are a couple of things that we need to cover in Fusion to put this whole desk together. And let's begin with the leg of the table that I chose. So this is the IKEA Trotten desk, as I've mentioned previously. So this is just the mock-up of the leg and what will mount direct to the leg. This here, let me just remove this cover. This here are just two end stop switches that are tied in parallel just in case one fails. And this is essentially what we will be using for homing the desk. So when we press the home button, as you've seen in the interface, the desk will go down until these switches are triggered, and at that point that's the lowest height of the desk, and the software will set the height, the actual height to 70 or 75 centimeters as you've set it in the interface. Besides that, we have the motor and the motor mount. So this is just a simple cover for the motor. Let's remove it to see inside. And this is the mock-up of the motor that you've already seen on the bench, with a simple mount that I've just cut out of a piece of plastic and that I will 3D print. To move on, then we have the encoder. Let me remove this cover here. It has the same hexagonal shape as the IKEA Trotten desk, so a simple 6mm Allen key can fit inside here. It's a bit larger just because of 3D printing, so it's 6.5mm. It mounts to this bracket here, and this bracket then directly mounts to the table. In the end, we have the physical interface, which you can see here. This whole part here sits underneath the desk, so outside the desk, the only part you can see is actually just this. The small display that will show you, which also angled a bit, the current height, the memory you're going to, and so hidden below the surface of the desk will be the buttons which will go here. I added this small lip here, which you can remove if you don't like. I added it because I don't want to trigger any of the buttons by mistake, for example when rotating the chair around or just hitting it by an elbow. So this is just the protection. The desk will come up to here and you have this here, so you really need to want to push these buttons for anything to actually happen. And if we flip this upside down and remove the cover, this is the perf board where we're gonna sort all of our electronics, and this is the motor driver with all of the cables coming in to here. So that would be it. We covered all of the things: electronics, all of the software, and all of the mechanical stuff. The only thing left to do now is to assemble everything. With all of the individual parts figured out, it was time to assemble it. So let's see how this turned from a sitting desk into this standing desk within about 3 hours or so. Space in the room is limited, but I made it work. First had to clean the stuff up and remove the old legs from the table. After that, I could bring in the motorized legs and align them up with the tabletop. After that, it was just wiring. I managed to even burn up a main power supply, as you will see in a moment. But I made sure that everything worked, and then finally I could just flip up the table and clean it up before doing a bit more work than I initially planned on doing. While the assembly might seem done, there's actually something more I wanted to add. So these are the parts you've already seen that I 3D modeled, but what about this? So this is how I imagined the whole desk looking. I didn't just want a desk that I can get lower or higher, I also wanted to make it completely custom. So this is the same desk surface that I am still using and I'm gonna keep using. But because the IKEA desk that I bought came with another smaller surface, I thought, why not utilize it and make some shelves? So if we remove this, I'm gonna make this whole construction out of aluminum extrusions, have a big monitor shelf here, and on the bottom here gonna have a shelf for all of the chargers, outlets, so I want to see the least amount of cables as it's possible. And it will all be mounted just using these 4040 extrusions with 6M6 screws, which will be more than strong enough. This will also let me do cool stuff like mount monitor arms, mount laptop arms to the extrusions, lights, cameras, electronic gear, and anything else that comes to my mind. So let's finish up the assembly now. And that's what it took to convert the desk from sitting to this standing desk. I'm incredibly happy with how it turned out. The only issue I'm having with it is that it's kinda loud and encoder needs a bit more fine tuning, but that's mostly due to the motor from the drill that's just loud as it is. I mean, the desk sounds like a drill. What can you do? I'm not complaining too much because it's really working nicely. Both the interface that I have on the web as well as this interface here. I'll play you some clips of it going up and down. I'll just won't play the audio so I don't actually deaf you with it. The greatest thing about this desk is that it's fully modular because of the aluminum extrusions, so I can have custom mounts for things like my calipers, for my USB isolator, so it's gonna be a work in progress desk. The next thing I'm making for it is actually a laptop arm, a custom one with 3D printed parts that will go here so the laptop doesn't take up so much desk space here. Thanks so much for watching the video. If you want to recreate this desk yourself, you can find all of the files from CAD to code to all of the electronics down below on Element 14 community. Also, if you have any suggestions for me to what I should do next to the desk, besides the laptop arm, if you want me to add some lights or any other cool ideas, please leave them down below in the comments and I'll do an update post on how this desk turned up. Until next time, see ya!